The second step of the Luenberger type normal form is as follows. So I repeat some things from the last video. This is the P matrix which we have performed from the selection rule. It is the P matrix, and because of the P matrix contains only independent columns, the inverse of the P matrix is always exists. We calculated 3 in these indexes. Sigma 1 is 3, sigma 2 is 4, and sigma 3 is 6. We are going to use them. How? This is the first step of this video. So we are going to calculate the inverse matrix of P, and the third, the fourth, and the sixth rows of P inverse is going to denote by Q1 transpose, Q2 transpose, and Q3 transpose. So we calculate the P inverse, and the third, that is the sigma 1, the fourth, that is the sigma 2, and the sixth, that is the sigma 3 rows of P inverse must be selected. This will be Q1 transpose, this will be Q2 transpose, and this will be Q3 transpose. So we are going to get 3 row vectors. And with these 3 row vectors, we are going to set up the following transformation matrix, which is denoted by T. And there are 3 main blocks of this matrix, according to sigma 1, sigma 2, and sigma 3, or according to the column vectors of the matrix P. So the first row of the T will be Q1 transpose. The second row here will be Q1 transpose A, and then the third is Q1 transpose A square. This is the first block of the transformation matrix T. The second block is just Q2 transpose, and finally the third is Q3 transpose and Q3 transpose A. If we use this transformation matrix T, we are going to get a new representation of the state space model. So it will be A tilde, B tilde, C tilde, and D tilde. These are the transformed representation of the system. It is well known that A tilde is T inverse, B tilde is TB, C tilde is CT inverse, and D tilde is equal to D. And if we use this transformation matrix, we are going to get a very interesting formulation of the elements of the system. So if we get A tilde, we are going to get an A tilde matrix as follows. So these diagonal elements will be 1, except the rows of sigma 1, sigma 2, and sigma 3. So the sigma rows are some numbers, containing some numbers, which I denoted here some stars. So these are general numbers from the real number set, of course. All the other rows will have a special form, which I highlighted here. So the first diagonal, first upper diagonal, will be exactly 1, except the rows of the denoted by sigma indices. And in the B tilde, we also have a special form. All the elements are equal to 0, except the rows denoted by sigma 1, sigma 2, and sigma 3, and these rows result in an upper triangular matrix like this one. The upper triangular matrix has a diagonal containing unit elements, and all the other elements in the upper triangular matrix will be some general numbers. And because of this very special form, this term always have the inverse matrix. The inverse of these elements exists, and it will be very, very important when we use this normal form in the calculations later. So the result of this transformation matrix is a special form of A tilde and B tilde. So the A and B matrices of the representation of the system. C tilde and D tilde are not very important for us from this point of view, because we are not going to use it in the controllability questions. So this is the Luenberger type controllability normal form. If we have the system representation of A, B, C, D, and we are going to use the transformation matrix T, as I mentioned here, according to the Luenberger type normal form and the selection scheme, we are going to get a very special form of the transformed system representation of the equations.